All right. Hello, everyone. We'll start off with today's meeting. Today will be about predicting income. So a lot of this will be related to the sky is no limit competition. So we'll be going over something similar to what you might have to do if you decide to participate in the sky is no limit competition. So kind of going through the motions, what you'll be looking for, the process, and kind of learning more about neural networks along the way. And so we'll start off. So unfortunate. Oh, there we go. Okay. So before we would like to make an announcement about our next meeting.
Hold the speaker.
Go.
All right. So this Thursday from 6 to 7, we'll be having our first speaker event of the quarter, our first of 5. It will be held on Zoom. We're going to be hosting Tej Lakoum, who's a product manager at Oracle. He'll be talking about his work using cloud applications and developing cloud applications for Oracle and how he's using artificial intelligence to do that. So we're looking forward to seeing you all there. And hopefully you guys ask lots of questions and get a lot out of it, network, and really learn from. So we're looking forward to seeing you guys there. And yeah, let's get on with me.
Sounds good. Again, this will be on Thursday. Please come. You'll learn a lot. If you have any questions, you can ask it there, and hopefully you can get a lot out of it. So perfect. So we'll get into kind of the meat of what we'll be talking about today. So majority of when you start on these projects is you'll start off by looking for a data set. In this case, I've already chosen a data set. This is considered the adult data set. It's called the adult data set because it is US Census data from, I think, 1980, somewhere around then, about different adults living in the United States. And kind of gives you some information about them. And then the result would be to try to predict what their income is. So in this case, is a Boolean value of whether or not they make greater than or less than $50,000 a year. And so we can see here all the data is given to us. In reality, it's a bit more, but for the data set that we'll be using in the Colab notebook a little bit later, this is all we'll be using just for simplification purposes. So we have the age, the education numbers. This is what their highest grade of education that they've gotten, their race, sex, capital gains, capital losses, and then hours per week worked. And so using this data, you can hypothetically predict how much income that person is making. So another way we can view this is here. And so this kind of just shows, again, the different parameters that you're given before you're able to identify and predict the income of these specific people. So for instance, the person up here, the first person, notice how sex is considered to be zeros and ones. This is a Boolean. This data set has been a little bit pre-processed to hopefully decrease the discrimination or something related to that. So instead of it being multiple classes, it's just Boolean of white versus non-white. If you want to know a bit more, we could talk about that afterwards. But we have race as a Boolean, sex, it's binary data. Again, that's just what the data set was at the time. And then age, the education number, and so on. So I'll give everyone, say like 5 minutes or so to talk amongst yourselves. Given this data, what would be your steps to coming up with the income? Do you have to do any more processing of the data? What kind of model would you use? And kind of the steps you go about it. So we'll let you guys discuss amongst yourself, and then I'll ask someone to share in a second. Does anyone need more time before we continue on? Looks like everyone's discussed. All right. Would anyone like to kind of talk about their idea about how they can use this data set to predict income or what their ideas were? Anyone like try this one out? Yeah.
Yeah, I was thinking just like general rules of how many hours they were working.
Mm-hmm.
If they're investors, obviously you need to know the capital response.
Mm-hmm.
That
Yeah.
does contribute to income. And then their educational numbers, like the upgrade higher, whatever that may be. Because sometimes people who don't go to college earn more than those who do go to college, and so much overcrowd. So
Mhm.
it does kind of fit forward. You kind of see the perfect factor. You get outliers, you take a step back. But you should be able to see a trend.
Yeah, absolutely. As you said, there's definitely going to be some form of a trend. And how good of a trend it is, I mean, it depends on the data and everything. But one of the good things we learned about previously was a version of linear regression using this data to find that trend line to see, hey, maybe if we notice that the older they are, the more income that they're making. And so we could see this all in a linear regression line. That's one really great model to use for this. And definitely a lot of good points there on how to be able to predict the income for this model. Anyone else want to give a shot at this one? Again, there's pretty much no wrong answers. You can even say just guess randomly. You'd at least have a 50% chance of getting it right. I mean, anyone else? All right. Well, today, as I mentioned a bit, we'll be talking about neural networks and how we can use neural networks to solve a problem like this. So real quickly, neural networks are essentially supposed to simulate how human brains function and work. And so there's a bunch of interconnections that we'll see in a second. So here we have a quick diagram as to what a neural network will look like. These can vary a lot depending on how complex your neural network will be. And so we can look at the different parts. So every single one of these columns are considered a layer, and these layers consist of neurons. Each of these is a neuron. If you remember from last week, we talked a bit about perceptrons. These are very simple. A perceptron relative to a neural network is like one of these connections between these layers. It's a bit smaller, whereas neural networks are a big collection of them. So as we see here, we have our input layer. So in the case of our predicting the income, our input layer would be all of our parameters. So think age, education number, capital gains, capital losses. All of those would go into each one of these neurons. So each neuron basically stores a value that'll be used in the next layer. And so what is the next layer? Well, the next layer, we kind of think of it as a collection of what's called hidden layers. These hidden layers can really be anything depending on how you decide to build the neural network. And so there could be any number of them. They could be different number of neurons per layer. It really, again, depends on how you're making it. So once you have all of these hidden layers, you then bring it out to a final output. This output depends on what you're trying to predict. So in the case, again, with predicting income, you're predicting just true or false, meaning that your outcome would only be one neuron because it's either going to be 0 or 1 or, something in between, depending on whether or not you're talking confidence or probability. On the other hand, if you're trying to predict whether a picture was of a dog, a cat, or a snake, you would want maybe 3 outputs, right? The probability it's a snake, probability it's a dog, or a cat. And so each of these layers serves a purpose in that we have our input layer, which is the parameters, output layer, which is what we're trying to predict, and the middle hidden layers, which will be used in training. As you can see here, there's a lot of interconnections. We're about to go into what do these interconnections mean and how they help define what each of these neurons do. So this is essentially how we calculate what a neuron is, how everything works together. So I'll go over this briefly, and then the next slides, I'll go a bit more detail. So here we have all of our inputs. So if this was the first layer, these inputs would be the parameters, think age again, capital gains, capital losses, and we multiply them each individually by a specific weight. These weights are values that will be changing throughout the training process. So as we train our model, these values will change to help come to a good predictive kind of formula. And so just know that these values are going to be continuously changing during the training model. And then eventually, once we've fully trained it, these numbers will be stationary. They won't change at all once it's been fully trained. And then you can then throw in whatever input you want, and it should predict correctly or attempt to predict correctly. Once we've multiplied them across, we get a bias, or we get a sum with a bias. This bias number works exactly the same way with the weights. where it's a value that changes while it's being trained. And once it's finished training, you get a stationary variable, a static variable, and we get a almost final value for the output of our neuron. But first, we must throw it through an activation function. Again, we'll talk all about this in the next slides. So look at the first step again. So we start off with our inputs. So for instance, maybe the age being 25, capital gains being a 7, capital losses being a 10. These weights, they'll start off as random values. So maybe they'll all be 1. So you multiply them all across by 1, you get whatever value. But let's say we have trained it a little bit, maybe not fully trained, but currently these values for the weights are 0.4, 2, and 0.5. So we multiply across and we get these temporary values corresponding to each of the neurons. So with those temporary values, we can then combine them together. So think about in the previous slide. So that's now that we have each of these neurons and we're trying to then calculate this single neuron here. This is the combining step where we add them all together and alongside a bias value. This bias, again, works exactly the same way as weights where they get trained and they'll change until you have completed your training. And then we'll get to our temporary value, which will be used in the final step with our activation function. This activation function could really be any formula, but there's a lot of different functions here that are used for different reasons. In this case, we can be using the sigmoid function. So it takes a 2, outputs a 0.88. We'll show you what that looks like in a second. So this is the different common activation functions. You don't have to have them memorized. It really depends on what you are looking for and what you're trying to get out of your model, which depends on which one of these activation functions you choose. We talked about it a bit last week, but we'll go over it again. So main thing you want to look at is the range. So let's say you are predicting whether or not something is true or false. If you're trying to predict whether something is true or false, you want your output to be either a 0 or a 1, or something in between. Which in this case, we would like to use our sigmoid, because sometimes once you add everything together with the bias, you might get a value again of like 200, right? And you don't want to use the 200 to predict whether it's a 1 or a 0. So we kind of use a activation function to normalize it a bit. So here we have a sigmoid function, which helps normalize it so that such that it's between 0 and 1. And again, we can see the same thing here with tan h, which is -1 to 1, and then ReLU, which is a very simple max, either going to be 0 or whatever the value is that's greater than 0. So sometimes you would want to use different ones. It really depends on the situation you're talking about. Beyond just the simple looking at the range, the output of this, it's a bit harder to identify which one you want to choose, and it comes more to fine-tuning the model once it's already been completed. This brings up in the next step. So now that we know how each of these neurons are connected together, which was that function we talked about a bit earlier, what do each of these layers mean? How can we interpret this in an easy way? Well, one easy way to think about it is in the square detection situation. It's very unlikely that a situation will ever be this simple, but this is just one way of viewing it. So let's say we take as an input a picture of pixels that are either on or off, so 0s or 1s. And we're trying to detect, does this picture contain a square? So we kind of flatten this out into a one-dimensional array. So just stacking all the different layers of this into one layer and putting into our input layer. Oops, that's the wrong direction. Then we can look at it at the first layer. So this first layer might only look at a very tiny subset of pixels. And so in the case, it just looks at these first 9 pixels. And that could be just that very first neuron from the previous one. So maybe this first neuron will look at just the pixels here. And we can notice that, hey, just looking at this, it looks to be maybe a short, stubby vertical line, some sort of thing like that. And we're able to identify this as a vertical line through the functions we talked about earlier. So the weights will hopefully be trained in a way that it's able to detect a small, stubby vertical line. And so we'll do that for every single one of those neurons within that first layer. So every single one of those neurons might detect some form of a stubby line. The next neuron will then look at all the previous neurons from the previous layer. So maybe this one might notice, hey, look, this one notices that there's a stubby line. This one notices that there's a vertical stubby line. And this one notices that there's a stubby vertical line, meaning there's probably a long vertical line segment. And maybe this one notices, hey, there's a bunch of horizontal stubby lines, and it detects, oh, there must be therefore a long horizontal segment. And then the third layer might detect, hey, there's a vertical segment next to a horizontal segment, therefore there's a corner. And you keep going on so forth and so forth until finally you get to, hey, look, there are 4 corners, therefore I'm going to predict there is a square in this image. And so you can use each of these layers as a different point of kind of solving a problem. And that is kind of the most optimistic way of looking at a neural network. Usually it is not the case. So for instance, in the income generation, it's going to be a lot more complicated and really hard to tell what each of these layers represents. But when it comes down to just learning why we have multiple layers, that's kind of the main idea. So that gets us to the next point. So I talked a lot about training. Well, what does that really mean? And so what that means is we have these variables, these weights and biases. So any interconnection of neurons has tons of these weights and a singular bias. And so each of these need to be specifically changed such that we have a model or this really, really big function or a black box that's able to identify and predict this income. So how do we train these values? Well, yeah, the way we train it is through an optimization problem. Optimization in this case would be like trying to find the minimum or the maximum of a given function. In this case, we're trying to optimize or minimize the loss. Loss can be calculated pretty easy in this example. So let's say we have this predicted income versus the actual income. And we see out of the 10 predictions here, we got 3 out of 10 incorrect. So that's where all of the arrows are pointing to. So these 3 people, we got them wrong. That means we'll just say that we have a loss of 0.3, something pretty simple, right? Well, our goal would be to get that loss to be lower. So that means in what ways do we have to change our weights and biases to decrease our loss? And that is where we come up with gradient descent. Gradient descent is a way of finding which direction to tune these weights and biases. So if we look at this graph right here of loss and a value of a singular weight, which direction do you guys think we'd want to change the weight? Do we want to increase it or do we want to decrease it to minimize loss? Someone can just shout it out. Absolutely. We want to decrease our weight because if we notice here, we decrease our weight, meaning that we move left in the x-axis, we would actually be decreasing our loss. And so one way we can look at this is through the concept of a gradient or the derivative, because in our computer models are not actually going to be drawing this graph as we see here. This is just for our own imagination to view it. And so what it actually does is it looks at how do each of these weights actually affect our loss function. So that goes into optimizing. And notice, hey, if we actually decrease our weight, it will decrease our loss as well. So it will change our loss just a little bit and move it, or change our weight and move it to the left a bit, and therefore also decreasing loss. And then it will just keep doing this. Every single time you have a new training session or an epoch, we will change the weights to hopefully decrease loss. So you see here, again, which way do we want to move our weight? Yes, left. We want to decrease again, and that will get us to our minimum point. And we'll keep doing that until hopefully we can find the absolute minimum. Can anyone identify a possible problem with this gradient descent concept? Yes. Yeah, sure.
The local minimum.
Absolutely. Local minimum versus global minimum. So for those who don't know, local minimum is a point in the graph where there is a valley, but it's not the absolute lowest in the graph. So right here would be an example of a local minimum. So for instance, if we had our weight up here and we said, okay, which direction do we want to move it? Oh, we want to move it to the right. So loss would decrease. And we say, oh, let's do it again, right? And we get stuck here. That's a bad optimization, right? We want to find the absolute minimum. So often we'll see examples of this in our models where it optimizes, it says, hey, I found the most optimal variables, and you realize it's not very accurate. And it's often because it accidentally finds these local minimums when solving for our optimal weights. So how do we go beyond that? Well, I like to think of it as a concept of momentum. So think of, let's say you rolled a ball from here, right? Well, when you roll a ball, it goes down, but it keeps its momentum. It keeps its knowledge of the previous direction it was going in, and it will try to keep going that direction. So hopefully it will go up the hump to hopefully find that absolute minimum. This won't work perfectly, but these are just simple tools that we can use to kind of find the absolute minimum. You don't have to have this memorized, just the concept of the program using gradients, or also known as derivatives, to be able to identify this minimal, or this direction that we need to change our weights to get a optimized loss. So as we can see, this is what it looks like with two weights, or two things we need to optimize. It starts to get really confusing about which direction we need to change our weights. Now imagine with even like a medium-sized neural network like the one that we've been looking at here. Every single one of these lines is a interconnection, therefore a weight that needs to be optimized. And so just look at this small one, there's around 1,000, I haven't calculated it. No, hundreds. Well, the numbers can get huge for the amount of weights and biases that we have to optimize for. And so these things become very computationally expensive. And oftentimes when you try to train a model, it will take a long time. And this is why, because trying to optimize and find the derivative of all these small interconnections takes a long time. And so that's why we have this gradient descent. So we know which direction to go instead of just picking a random thing and testing and see how that works. So that brings us to, I am going the wrong direction. Final kind of overview as to what our neural network is. We start off with all of our inputs. So with the income, that's all our parameters. It gets put through a bunch of different layers where when we train it, these neurons will then hopefully learn something about the data to optimize for a smaller loss, so more accuracy. And then it will eventually have our output, which will be our prediction. Any questions before we go into the actual notebook where we can play around with the code and actually see what this looks like in a Python environment? No questions? Perfect. Let's move on. So if everyone can go to this URL right here to find our notebook. If you want to be able to save your data, I suggest creating a copy of the notebook, because if you don't create a copy, it won't save any of the code that you've done. So, we'll start off with that. We took a poll before, and we've seen a couple people said that they wanted us to go over how to do these notebooks. Can I get a raise of hands of who wants to go through it together versus how many people want to do it individually? So can I get a raise of hands of who wants me to go over it with everyone? Okay, that makes it obvious. All right, let me set it up and we'll start from there.